minutes past 9. Staring into space a little bit later than what we normally would on this Friday, but it's all good with Dylan Storey. Thanks very much to the Auckland Stardome Observatory. Good morning, Dylan.
Good morning, Wammo.
Good morning. And a big week for space gazers and for people in the Northern Hemisphere with the Northern Lights going crazy. Solar storm.
Yeah. So that's been on the news. That's been the big thing on the news, is solar storms causing auroras. But it's not just the northern hemisphere. The auroras are exactly equal in the northern and southern. But most of the land mass in the northern hemisphere is closer to the pole, so you're more likely to see it over there. But certainly, South Island and New Zealand, you've got just as big a chances of seeing the aurora.
Oh, okay. But
Further south, the better.
It feels like, though, we're told that it seems to be hitting the Northern Hemisphere more, or is it just because there are people up there to see it?
That's just because there are people there to see it, yeah.
Okay, all right.
There was studies done by NASA where they flew planes simultaneously over the northern and southern, north and south pole, and they mapped the aurora, and the results was that the aurora is identical, so it's an identical mirror from the North Pole and South Pole.
Okay, there you go. So what causes it?
Well, it's these storms on the sun. So imagine the sun as a massive nuclear reaction. The fiercest part of the reaction is going on in the core, and so different sort of bubbles of heat come up and they rise up towards the surface, and the electric charge from them gives off magnetic fields. So particularly large convection currents coming up to the surface will create particularly large magnetic fields, and sometimes they break the surface and sort of fly off out into space. So we've got these kind of bundles of charged particles racing off through space. Now, they don't move at light speed, so the light from them gets here much quicker than the particles. They take about 18 hours to get to Earth, whereas the light takes about 8 minutes. And so they travel through to Earth, these charged protons, so little particles, and when they get to Earth, they get deflected. So they're coming out at Earth all the time, basically, but when there's these solar storms, you just get a sort of a bigger bundle of them, and they hit Earth, they get deflected by our magnetic field. So when we get a particularly large one, we get a particularly large dose, and imagine the Earth as a magnet, which it basically is in space. So you've got the magnetic field lines curving around either side, and so if a particularly large bundle of particles hits the side, they're deflected round, and then they sort of all come in close where the magnetic fields come together, which is on the poles.
And effectively, it's an eruption though from the sun, yeah. Yeah,
it's a kind of I guess you could call it an eruption, yeah.
Okay, yeah.
Okay. An eruption of particles. So at the poles, they make it close to the planet. When they get close to the planet, they hit the atmosphere, albeit the atmosphere way up high.
Yeah.
And because they've got an electrical charge, the atmosphere has electrical charge, tiny little electrical reactions take place, giving off tiny little bits of light. But there's so many of them that they can appear as these coloured lights.
Right.
So that's what the aurora is, tiny little electric charges high up in the atmosphere.
Okay. Now, they have the potential, of course, obviously they're very pretty, but they have the potential to be more than that, can't they?
Yeah, I mean, there are a lot of satellites up in orbit. A lot of those satellites, including the International Space Station, pass over the poles. They've got a kind of semi-polar orbit, so they become reasonably close to the place where these particles come in and interact with the atmosphere. And if some of these particles hit a sensitive piece of electronic equipment, they can cause a glitch. But satellites these days are built with multiple redundancies, so they're sort of built to take these solar storms. And so, if there's one little glitch in one tiny circuit, another one will step in to take its place, and so on. So it can cause problems, and I guess the problem comes that so much of our infrastructure on Earth now is controlled by satellites.
Yeah.
So
GPS and all that.
GPS, the internet, communications, military stuff.
Sky TV.
Oh, I mean, consider the implications if something went wrong with Sky TV.
Exactly. But there's also the potential, of course, not just for satellites, but also for electronics based on Earth.
Yeah, very small. Very small.
Talk it up, Dylan. Come on. Major disaster potentially on the horizon.
Yes, there is a chance that there could be major disaster, that's right. I won't go into how big that chance is.
Really? But hasn't something happened like early part of last century, North America had... or no, actually it wasn't even the early part, it was in the 70s, wasn't it? That an electrical grid was knocked out in Canada?
Yeah. And I think that the control systems for it were particularly fragile to magnetic and radiation fluctuations. So, that's happened. It was a big disaster. It's built into the textbooks now. It really is a rare event that any of the sort of effects of these particles.
But the sun right now, we're told, is entering a period of heightened activity.
Well, that's just the thing. Yeah, it is entering a period of heightened activity because the sun goes in cycles of 11 years. And so we've got solar minimum in the middle of the 11 years and solar maximum. Solar minimum was, must have been about 4 years ago. So we're coming into solar maximum in the next couple of years.
Yeah.
So, yeah, we will get more of these sunstorms. But they're by no means unique because it happens every 11 years. We get this solar maximum, and this isn't a particularly big one.
Okay, so it's not out of character. People shouldn't be alarmed.
No, exactly the same thing would have happened 11 years ago and the 11 years before that.
Is it just because 11 years ago not everyone was connected to the internet, so not everyone knew what was going on and can only be told by newspapers? And
that's pretty much exactly it. Well, there is more sophisticated equipment monitoring the sun now. There's the SOHO satellite and the stereoscopic satellites observing the sun. So basically, as well as the communication spreading faster, we're also getting much more detailed observations of the sun.
So it may appear as though there's more solar activity or it's out of the ordinary because everyone's sort of talking about it. But it's actually not the case. It's just falling into pattern.
That's right. Well, the highest peak in sort of modern times was actually in the 50s. So we're not up at the level that it was in the 50s. But of course, we've got much more sensitive electronic equipment now than we did in the 50s. So,
true.
Yeah, the implications are potentially more serious.
Your valve radio in the 50s probably wasn't going to be affected quite the same as your GPS phone these days.
Yeah, exactly.
All right. Well, if you're in the deep south, in the South Islands, or you're watching this video anywhere up in the deep north or deep south, then you can go and check out these lights. Check out the light show.
Yeah, try and have a look. The aurora.
Yeah.
And of course, Stardome Observatory, great place to observe the sky and see things through telescopes that you wouldn't normally see.
Indeed. And Dylan Storey on Twitter, if you've got any more stories to talk about with space news and all that kind of stuff, then go to it with Dylan on twitter.com/Dylan Storey.
Exactly.
It's now